Okay, lesson 7. We're going to do some more max-min problems. Remember, you guys are writing your quiz on this stuff tomorrow. And tomorrow we'll also be starting the next chapter on curve sketching. So a lot of what we did in this chapter is going to lead us into sketching curves like what, Brighton? Who? Like finding where functions are increasing or decreasing, also finding the location of max and min points. We'll use those for sketching curves. But another application of max and mins are these max and min problems. So we looked at one similar to question 1 on Friday. We'll look at a few other ones as well that you haven't seen before. Perimeter of a rectangle is 24 centimeters. Determine the dimensions that will maximize the area and also determine the maximum area. So an application of this would be similar to one we looked at on Friday, where a person had only so much fencing to make a dog run, and they wanted to maximize the area. And so that would make sense that you might want to do that. But first we have to come up with an expression for the area, and then we differentiate it in order to find out where that maximum area occurs and what it is. And so remember, you need to have an equation that only involves one variable. So we'll start with the rectangle. And if we say that W is the width and L is the length, and again, we need to come up with an expression for area in terms of only one variable. Right now, area would be width times length, but we need to write one of those in terms of the other. And either we're going to write length in terms of width or width in terms of length. And we can do that by using the fact that the perimeter is 24 centimeters. Perimeter is a distance all the way around. You add up all the sides. So 2W plus 2L will be 24. And so now we will isolate either W or L. It doesn't matter which one we do. We just choose to get L by itself. By subtracting the 2W from both sides, it'll become a negative 2W over on the other side. And then dividing both sides by 2. And so there's an expression for the length in terms of width, the W. So now we can say that area is length times width. L in terms of W would be negative W plus 12 times W, the width, gives us negative 2W squared plus 12W. So again, you did something similar to this in 20-1 in quadratics. Okay? The difference, though, is that in quadratics, then we found the maximum of this quadratic, and it has a maximum because the quadratic opens downwards. We know that because the initial term is negative 2W squared. So in 20-1, you completed the square. You wrote this in vertex form, a bracket x minus p all squared plus q, in order to find out where the maximum was and what it was. But now that we've learned about derivatives, we can differentiate this. So dA by dW will be negative 4W plus 12, and you want to find the critical number for that. Where does it equal 0? Yeah. Pardon me? Oh, that's a very good point. That's a good question. I have no idea why. Yep. Thanks for bailing us out. Okay, so that'll just be negative W plus 12. Negative 2W plus 12. Yeah, negative 2W plus 12. The derivative is negative 2W plus 12. So the critical number It will be when that equals 0 or when W equals 6 centimeters. And the length is negative W negative 6 plus 12. So it turns out in this case that the perimeter, or the area is maximized when it's actually a square. A square is what will give us a maximum area in this case. And the area, which is length times width, would be 6 centimeters by 6 centimeters, or 36 square centimeters. So the maximum area occurs, actually let's say this, maximum area of 36 centimeters squares occurs when the dimensions are 6 centimeters by 6 centimeters. Sure. Yep. Okay. This next one says a box has square ends and the sides are congruent rectangles. Total area of the four sides and two ends is 96 centimeters squared. So we're given the surface area. We want to determine the dimensions that will maximize the volume and also determine what that maximum volume is. So the volume of a box is length times width times height. But again, we need to have this in terms of only one variable. But we do know that the ends are square. So if we draw a picture of this, so when we say the ends, it means the tops and the bottom. And we saw one similar to this on Friday. So if we say that the base or the top measures x by x, and then we'll have h the height. And the four sides are congruent rectangles. We're told that the sides are congruent rectangles. So now we can say that volume equals x times h, or x squared times h. But once again, we need to have the volume in terms of only one variable. Right now we have two. So we can use the fact that the surface area is 96 centimeters squared. So the surface area of this box would be your top and bottom, which are congruent squares. They measure x by x, and there's two of them, so 2x squared plus, then you have four rectangular sides that measure x by h, so 4x by h, and that will equal 96, because we're told that's what the surface area is. This allows us then to express h in terms of x. We can get h by itself. I'd start by subtracting the 2x squared from both sides, and then dividing everything by 4x. So that'll give us negative 1/2 x plus 96 divided by 4 is 24 over x, or 24x to the negative 1. So that's what h is in terms of x. So now we can say that the volume is x squared times h, which is negative 1/2 x plus 24 x to the negative 1. So that'll be negative 1/2 x cubed plus 24 x to the 1. So there's volume. And now we will differentiate that. It'll be negative 3 over 2x plus 24. And we want to find the critical number for that. Where does it equal 0? So if we add the 3/2 x to both sides, it would be yes. Thank you. And now we need to solve for x. So we can divide both sides by 3/2 or 1.5. And x squared will equal 16. And therefore x equals 4. And then we can write the height, or figure out what the height is, because we know that the height is negative 1/2 x plus 24 over x. X is 4, so it's negative 1/2 times 4 plus 24 over 4. Negative 1/2 of 4 is negative 2 plus 6, which is also 4. So again, it turns out that the box is actually a cube, because the base, which is a square, measures 4 by 4, and now we've seen that the height is also 4. And so when you find the volume by going length times width times height, 4 times 4 times 4 is 64. So the maximum volume of 64, and this is in centimeters cubed, occurs when the box measures 4 centimeters by 4 centimeters by 4 centimeters. Yes, Brighton. And you can't always assume that. Also remember that in some of the questions we saw last day, we didn't use all 4 sides because the dog run used the garage as one of the boundaries. And you can also have scenarios like this next one where there is no top on the box. So that changes things as well. This box only has 5 sides. But again, it has a square base and congruent rectangular sides. Also in this case, you're given the volume, and you need to determine the dimensions that will minimize the surface area. So again, if we start by just drawing a diagram, and like we did before, we can say that the box measures x by h. But also in this case, you're given the volume. So that's what's different between this one and the previous one as well. The volume is x squared times h, and we're told the volume is 98. You want to minimize the surface area, so an expression for the surface area would be, again, your top and bottom which are squares that measure x by x. So that's 2x squared plus 4xh's. Before we can differentiate that, we have to write it in terms of only one variable. Right now we have two. And so we can do that by taking that first equation that we wrote for volume and get h by itself. H will equal 98 over x squared. So now we can sub that in over here. Oh, I'm really sorry. Yep, you are absolutely right. I am not focusing today. So 4 times 98, 392, and that will be x to the negative 1. So that's what we will now differentiate. There's an expression for surface area in terms of one variable. And we want to know where this equals 0. So remember, we could factor this. We could take out a common factor. When looking at the coefficients, you're going to have a common factor of 2. When looking at the variables, you take out a common factor that comes from the smallest power of x, or x to the negative 2, what our common factor will be. 2x to the negative 2. So when you divide the first term by 2x to the negative 2, the 2's cancel. When you divide the x's, you subtract the exponents. 1 minus negative 2 becomes 1 plus 2, which is 3. When you divide 392 by negative 2, what is that? 146, I think. 196. So it'll be x cubed minus 196, and then the x to the negative 2's cancel. And so our solutions will come when each factor equals 0. And for the first one, that will be where x is 0, which is not permissive, because then you wouldn't have a box anymore. The second one then would come from solving that equation. So that's where x cubed equals 196, and then we take the cube root of both sides. Cube root of that previous answer is approximately 5.8 centimeters. That's what x is. And then h is found by going 98 over that decimal squared. So 98 divided by the previous answer squared. And again, we always want to keep these numbers in our calculator. We only round our final answers off. So h is approximately 2.9 centimeters. And in this case, we're just asked to find the dimensions that will minimize the surface area. And also remember, we said last week that if the question says, determine the maximum or the minimum, the equation will work out so that you're going to get a maximum or a minimum. But remember, you can always use that number line that we've been doing to check, to make sure that you do get a max or min value depending on what you're being asked for. So in this case here, you want to minimize the surface area. So When x is 5.8, you should get a minimum value. If we choose a number to the left of 5.8, let's say positive 1, so the first factor will be positive, because 2 times 1 to the negative 2 will be 2 over 1 squared. 2 over 1 is positive. If we choose a number to the right of 5.8, a number like 6, well, I'm sorry, I have to finish this by doing the second factor. When x was 1, 1 cubed is 1, take away 196, it gives you a negative value. A positive times a negative is a negative, so the function is decreasing to the left of that. To the right, if we choose a value like positive 6, well, the first factor will be 2 over 6 squared. It's going to be a decimal, but it's going to be positive. And 6 cubed is greater than 196 when we check that second factor. 6 to the power 3 is 216. Take away 196 gives us a positive value. So it confirms that the function is increasing to the right of the critical number 5.8. So again, that confirms that the 5.8 is the position of a minimum point on that graph. Okay, so now we can say that the dimensions at minimize surface area are 5.8 centimeters by 5.8 centimeters times 2.9 centimeters. Yes, Brighton. Pardon me? Well, you wouldn't be able to do it, because this scenario, this equation we've just shown has a critical number of 5.8, and we've just shown that at 5.8 that has to be a minimum value. So with this scenario, it couldn't be maximized. Okay? Again, the problems will always be set up so that if it asks for a minimum, you're going to get a minimum. The only time that that might change is when we start looking at curve sketching, so it's not going to be a problem anymore, but when we're looking at curve sketching, a third degree polynomial will have a max and a min. We're going to be able to find out which of them is a max, which of them is a min by doing what we just did with the number line. That tells us that. Right, we saw one like this on Friday. Going to do a dog run, but the owner only has 60 feet of fencing available, and it makes sense that he want to maximize the area. So you've got the garage being used as one of the boundaries. You have 60 feet, so if W is the width, the length would be 60 minus 2W. And we want to maximize the area, so the area will be W times 60 minus 2W, or negative 2W squared plus 60W. There's our area. And that's what we need to differentiate. dA by dW will be negative 4W plus 60. And then we'll find our critical number. I'm making that equal to 0. So W will equal 15, and in this case it's meters. Then the length is 60 minus 2W. 60 minus 30 is 30 meters. So again, there's lots of different numbers that we can put in here for the width and the length. We only have 60 feet of fencing to work with, though. So we're saying that the maximum area occurs when the width is 15 and now we see the length is 30. And 15 times 30, I think it's 450 cubic meters. 15 times 30. Yeah. So a maximum area of 450 square meters occurs when the dog run measures 15 meters by 30 meters. So again, there's lots of different dimensions we could come up with by changing the width and the length. For example, if we said the width was 10 meters, then the length would be 60 take away 20. 10 by 40 only gives us an area of 400 square meters, which is less than our maximum area of 450. Okay? If we say that the width was, let's say, 18 meters, then the length would be 16 take away twice 18. 60 take away 36 would be 24. So 24 by 18 gives us an area of 432 square meters. Again, that's less than what we said was the maximum, 450. There's also nothing saying that you couldn't have decimals for these dimensions, which we've seen one like that today already, right? If we said that the width instead of 15 was 14.5, so then the length would be 60 take away twice 14.5. That will give us a length of 31. And the area, 31 times 14.5, again, is less than 450. Not much less, but it's less. So this will give us the maximum. So we didn't see one like this last class. Determine the points on the graph of y equals negative x squared plus 6 that are closest to the point 0, 3. So that negative x squared plus 6 is a quadratic that opens downwards, and it would have a y-intercept of plus 6. So if we were to sketch a graph, y-intercept of plus 6, we can find where the x-intercepts are by solving this equation. Remember, our x-intercepts are always where y equals 0. It's where negative x squared plus 6 equals 0, where 6 equals x squared, and x equals plus and minus root 6, which is 2 point something, I think. Try that again. Yeah, 2.4 approximately. I mean, we don't really need to know what those are. It just allows us to sketch a more accurate graph. Okay, so it looks something like that. Now we want to find the points on the graph that are closest to the point 0, 3. So 0, 3 is about right there. And we want to find the 2 points on the graph, there's going to be 2 of them, that are closest to that point. So we can kind of guesstimate where they are, but we're going to find out algebraically where they are. If those points are closest to the point 0, 3, the distance between them is minimized. And we have a formula for distance that you may have seen, would have been maybe back in grade 10, maybe not. The distance between 2 points can be found by using this formula. It's the square root of y2 minus y1 all squared plus x2 minus x1 all squared. It actually comes from Pythagorean theorem, where the line is like the hypotenuse of a right triangle. So with this line being the hypotenuse of a right triangle, you can draw a right triangle like that. And you're using points x1, y1, x2, y2 as the endpoints of the hypotenuse. But you don't need to know that. You don't need to know where it comes from. If you need it on a quiz or a test, you'll be given this formula. That is a distance formula. It can be used to find the distance between any 2 points. Now, in this case here, we have 1 point. The first point is 0, 3. The second point we'll just write as x, y. So if we say that x, y is 0.2, 0, 3 is 0.1, using the distance formula, y2 minus y1 will be y minus 3 all squared, plus x2 minus x1 will be x minus 0 all squared. Now, I'm going to square both sides right now because that'll get rid of the radical on the right. So I'm squaring both sides. So on the right side, I still have y minus 3 all squared plus x minus 0 is just x squared. So again, I got rid of the radical by squaring both sides. The issue we have, though, right now is that we've got two variables. We have the variable x and the variable y. So we need to do something. But remember, we're told at the very start, the equation is that y equals negative x squared plus 6. So we can use that as our substitution. Y equals negative x squared plus 6. So now we can plug that into our equation. Instead of y minus 3, it's negative x squared plus 6 minus 3. So d squared, whoops, I wrote the radical and I shouldn't have. I've already gotten rid of it. So d squared will equal negative x squared plus 3 all squared plus x squared. And so I can square out that binomial. I will get negative x to the 4th minus 6x squared plus 9 plus x squared. So d squared will equal negative x to the 4th minus 5x squared plus 9. Now I squared both sides to get rid of the radical on the right because it's going to make it easier to differentiate. And we can do that because the critical numbers for d will be the same as the critical numbers for d squared. Okay? The only difference is when we just had d equals, on the right side it was the square root of something. When we square both sides, the right side doesn't have a square root. But you see, it doesn't matter whether the square root is there or not. Because if you have 0 under the radical, the square root of that is still 0. Whether the radical is there or not will not change the critical number. The critical number comes from the argument, what's under the radical, when that equals 0. So it doesn't matter if the square root is there or not. If the square root is there, the square root of 0 is still 0. This just makes it easier to differentiate, which is our next step. D squared by dx. That tells us that we're doing the derivative. Is negative 4x cubed minus 10x. And we need to find our critical numbers for that. Where does it equal 0? So we can take out a common factor here, a common factor of negative 2x, which will give us 2x squared plus 5. And our solutions come where each factor equals 0. And because in this case x refers to a point on the graph, it can be negative. Yes. I can't hear you. No, because it comes from negative x to the fourth. Oh, I see. Yes, you are right, because we're squaring negative x squared. So yes, that should have been positive. So that's going to make that negative. Okay. So then when we solve each of these, it'll be where x is 0 and where 2x squared equals 5, where x squared equals 2.5, and x will equal plus or minus root 2.5. And the square root of 2.5 is approximately 1.58. And if we look at our diagram, it doesn't make sense if we let x equal 0. I mean, that is way down here. It's the origin. And we did a pretty good job of sketching our graph. So it's pretty easy to see that the distance between the origin and 0.3, which is 3 units, it definitely looks like it's longer than going from 0.3 over to the curve like we drew it. However, we can confirm that by again using our number line. We've got two critical numbers here. And I can go negative 1.58 and positive 1.58 but I don't really need to do that. I could just use the positive. I could put the negative 1.58 to the left, but it's not going to change our answer. We're just using this to confirm that we're going to get a minimum distance. The only thing that you have to make sure is that when you find a number to the left of 0, it can't be less than negative 1.58 because that is our other critical number over here. Okay, so whatever number we choose to the left of 0, we just have to make sure that it is not less than negative 1.58. But negative 1 will work. So if we let x equal negative 1 in the derivative, 4 times negative 1 all cubed will be negative 4. But then you're going to subtract 10 times negative 1. It's going to be negative 4 plus 10, which is a positive. It's going to be a positive value, which means the function is increasing there. After 0, a number like positive 1, it's going to be 4 take away 10, which is negative 6. So that confirms that the distance from 0 to 0.3 is a maximum distance, according to our derivative. A number greater than 1.58, a number like 2 cubed is 8, times 4 is 32. 32 take away 20 is a positive value. So that confirms that it's increasing in that interval. So from 0 to 1.58, it's decreasing. From 1.58 and on, it's increasing, which it confirms that there's a minimum at 1.58. So there's your answer. minimum distance occurs when x equals positive and negative, and I will use the exact value, positive and negative root 2.5, which we always use. And we can find out what y equals by using the equation. Negative x squared plus 6. So it's going to be negative root 2.5 all squared plus 6. Notice that only the x is squared, not the negative. So 2.5, the root of 2.5 squared is 2 points, so it'll be negative 2.5 plus 6, which is 3.5. So the points will be at plus and minus root 2.5, comma 3.5. So there's the points on the curve that are closest to the point 0, comma 3. Number 6 says a can is constructed so that it holds 2.5 liters of oil. Determine the radius that will minimize the amount of material required to construct the can. So we're trying to minimize the surface area, which again is a very practical scenario, right? If you're manufacturing these cans, you know that it has to hold 2.5 liters of oil, but you want to make it as cheap as possible to make these cans. So you want to minimize the surface area. So we need to come up with a formula for surface area of a cylinder, because that's what we're working with here. We want to come up with an equation to minimize the surface area, given that it holds 2.5 liters of oil and 1 liter has a volume of 100 centimeters cubed, 1,000, excuse me. So 2.5 liters would be a volume of 2,500 centimeters cubed. And the volume of a cylinder is pi r squared h. But we want to minimize the surface area. The surface area of a cylinder is 2 pi r squared, so that's for the circular top and bottom, plus the sides, which are 2 pi r h. And again, if you need this for your quiz, you'll be given it. But the surface area formula has two variables. We need to write it in terms of only one variable. So I can write h in terms of r, the radius, by again using the volume relation that we have. We can say that h equals 2,500 over pi r squared. Or 2,500 over pi r to the negative 2 if we want. That's what h is. So I'm going to let h equal that in my surface area formula. The pi's will cancel there. So that's going to make it a little bit easier to work with. So 2 times 2,500 is 5,000, and r times r to the negative 2 will be r to the negative 1. So there's our expression for surface area. And that's what we will differentiate. It's a derivative of area with respect to r, the radius, or derivative of surface area, I should say. So when we differentiate, it'll be 4 pi r. Again, there's only one variable here. Pi is a constant. So 4 pi r minus 5,000 r to the negative 2. I'm sorry. Oh, that's right. Minus 5,000 r to the negative 2 is correct. And we need to find our critical number for this, which we'll do by factoring. There is a common factor here of 4r to the negative 2. Which leaves us with pi minus 5,000 divided by 4, I think is 1,250. Whoops, that's not right, because when I divide the r's, r to the 1 divided by r to the negative 2 will be r cubed. So I need to fix that. Minus 1,250. So our critical numbers will be when 4r to the negative 2 equals 0, and when pi r cubed minus 1,250 equals 0. The first one will be extraneous. R can't be 0 because then you wouldn't have a cylinder at all. So we'll just solve the second one. So that's where pi r cubed equals 1,250. R cubed will equal 1,250 over pi. And then r will equal the cube root of 1,250 over pi, which is our answer as an exact value. We can certainly find out what it is as a decimal. The cube root of 1,250 over pi. Approximately 7.4 centimeters. But the exact value is what we would report. Minimize the surface area. Minimum surface area occurs when the radius is the cube root of 1,250 over pi. And that would be in centimeters. Okay. So we're going to finish off with this one. I think, yeah, there's one more, but we're not going to worry about that. There's not one like that on your quiz, nor will there be one like the last one on your test. So we'll finish off with this one. So you start with a 60 centimeter piece of wire, and it's cut into two separate pieces. One of the pieces is shaped into a square, the other shaped into a circle. Determine the length that each piece of the wire should be so that the area of the two shapes is both maximized and minimized. So just like we've said before, like if you have a third degree polynomial that you're finding the critical numbers for, you can have one point there where there's a maximum, another point where there's a minimum. So this is going to be one of those scenarios that we're going to end up with an equation that when we differentiate, we're going to get two critical numbers. One will be at a max, the other will be at a minimum, and we can use that number line to determine which one is which. But we're starting with a 60 centimeter piece of wire. So if we say that let's let x equal the piece, that doesn't look right. Yeah, I think it is. For the square. That would mean that y, or let's say that, let's do it this way, 60 minus x will equal the piece for the circle. Because you're starting with 60 centimeters of wire. You're going to cut it into two pieces. One will be shaped into a square, the other shaped into a circle. So if x is a piece for the square, 60 minus x will be the piece for the circle. Now, if it's a square, all four sides are the same length, so x over 4 will equal the dimensions of the square. Because it's a square, all four pieces are the same length. So if x is the entire length of the, or the perimeter of the square, then x over 4 will be the length of each side. So x over 4 is the dimensions of the square. It's x over 4 by x over 4. Now, if we're talking about a circle, right, we've got 60 minus x is an expression for the piece that's shaped into the circle. That means that is the circumference of the circle, right? The distance around the circle is the circumference. So the circumference of the circle equals 60 minus x, and the formula for circumference of the circle is 2 pi r. So you can solve for r, the radius, by dividing both sides by 2 pi. So there's an expression for r, the radius of the circle. And we need that because we want to both minimize and maximize the area of the two shapes. And the area of a circle involves the radius, pi r squared. So that's why we need r in terms of x. X is common, a common variable for both of our shapes. So again, we want to both minimize and maximize the area of the two shapes. So an expression for the total area of the two shapes, A, will be, well, first the square plus the circle. The area of the square would be x on 4 times x on 4, right? You take the length of one side and square it, or length times width will still be x on 4 times x on 4, or x on 4 all squared, plus the area of the circle. Formula for area of a circle is pi r squared, but we found r to be 60 minus x over 2 pi. So area will equal x squared over 16 plus, now we're not going to cancel the pi right now for the second term because the 1 on the bottom needs to be squared first. Okay? So we will cancel, but not just yet. So right now we're just simplifying our expression for area, and then once we have it simplified, then we can differentiate. But I need to square this expression, this rational expression. You square the top. As well as the bottom. It'll look like that. To square a binomial on top, you square the first term, you multiply the two together. That's where the negative 120, and double, excuse me, that's where the negative 120x comes from. And then squaring the last term, squaring negative x is positive x squared. So now we can divide out a pi there, just to make it a little simpler. So now we can say this equals x squared over 16 plus 3600 minus 120x plus x squared all over 4 pi. So I can simplify that second term. I can divide everything by 4 pi just to make it a little simpler. It also kind of gets rid of our rational expression so that when we differentiate, it makes it a little bit easier. So we could do that if we wanted to, or we could not. It doesn't really matter. And the reason it doesn't matter is because the denominator is a constant. So when you use the quotient rule to differentiate this, because the denominator is a constant, the derivative of the bottom will be 0. So it doesn't really matter which way we do this. But I said we'll divide it out, so let's do that. 3600 divided by 4, I think, is 900. So that'll be 900 over pi minus 120 over 4 is 30 over pi x plus 1 over 4 pi x squared. So the nice thing about this is now we've divided this up into separate terms. So to differentiate, we don't have to use any special rules because we've divided them up into special terms. We can just go term by term. I just want to check one more time to make sure that everything looks good here. 3600 divided by 4 is 900 over pi. Negative 120 over 4 is negative 30 over pi x. And then this 1x squared is divided by 4 pi. So I think that looks good. So now, dA by dx will be the derivative. It'll be 2x over 16 plus, this second term is a constant. There is no x there. The derivative of that is 0. This next term, negative 30 over pi x to the 1, when we differentiate that, it'll be minus 30 over pi x to the 0. And the last term, it'll be plus 2 over 4 pi, or 1 over 2 pi x. And we want to know where this equals 0. So I can do a little bit of simplifying. I actually have two like terms here, two terms that involve x. This first term, 2 over 16x, would reduce to 1 over 8x plus the 1 over 2 pi x minus 30 over pi equals 0. I can add these two together by getting a common denominator, and that'll be how many x's I have. My common denominator there will be 8 pi. So I need to multiply the first term, top and bottom, by pi. So that'll be pi x plus, I need to multiply the bottom, top and bottom, by 4 to make that 8 pi. And that will equal 30 over pi if I move the 30 over pi to both sides. When you cross multiply, you're going to get 30 times 8 pi, which is 240 pi, equaling, when you cross multiply the top left by the bottom right, you're going to get pi squared x plus 4 pi x. And you need to solve for x, which you can do on the right side by taking out a common factor of x, which will give us pi squared plus 4 pi, and then you divide both sides by that. And you should see that there is a factor of pi in all the terms. So we can divide everything by pi to give us a simplified answer of 240 over pi plus 4. There's the exact value of x. Now, we only get one critical number here, and that's fine. We actually have another critical number, which is the number 0. It is possible if x is 0, which means that none of the wire is used for the square. All of it is used for the circle. So that's one of our possibilities. What's 240 over pi on 4? Let's see. Pi plus 4. I think I said pi on 4. I should have said pi plus 4. So that's approximately 33.6. So I found that out because we need to check whether this is going to be a max or min there when x is 240 over pi plus 4. If we choose a number less than 33.6 but greater than 0, so I'm going to use the number 1. I'm going to let x equal 1. So we have a simplified expression for our derivative right there. And so when x equals 1, you're going to have 1/8 times 1, which is 1/8, plus 1 over 2 pi. You need to put the 2 pi in brackets to keep it as a denominator, minus 30 over pi. Gives us a negative value. So the function is decreasing in this interval. After 240 over pi plus 4, a number greater than 33.6, we could use 34 there. So it'll be 34 over 8 for the first term, plus 34 over 2 pi. And again, I need to put the 2 pi in brackets. Minus 30 over pi. 34. Oh no, 30 pi. Yeah, that's right, because there is no x for that term. It's just 30 over pi. And that gives us a positive decimal. So this tells us that you're going to have a minimum area, because to the left of our critical number of 33.6, the function is decreasing, the derivative is decreasing. To the right of it, it's increasing, which means we're going to have a minimum value, a minimum area when x equals 240 over pi plus 4. So this is a minimum area when x equals 240 over pi plus 4 centimeters. The area of the square, remember, is x squared over 16, which equals, again, x is 240 over pi plus 4. All squared divided by 16. So let me get back that answer again for our 240 over pi plus 4. There it is. I'm going to store that into memory because I need to square it. and then divide it by 16. So the area of the square is approximately 70.6 centimeters squared. The area of the circle and our expression for area of the circle was that's our pi r squared. Pi times 60 minus x over 2 pi all squared. So I'm going to plug that in. Pi bracket. Now we need another bracket for the, whoops, let's try that again. Bracket. I need another bracket for the 60 minus x. And x is memory slot A. That's divided by another bracket for the 2 pi. Close the bracket on the whole thing and square it. So that's approximately 55.4. You guys have a question there? Pardon me? I don't know. I have no idea. You'd have to look on Google. So then write it down as you're doing it, and then you have it. But yes, you can, for finding your critical numbers for the number line, you're going to use a decimal value, which is an approximation. Okay, so the total area is by adding these two together. So the 55.4 plus our 70.6. And just to be sure, let's go 5, 8, 4, 9, 8, 8, 9. We'll put them all in there. 126 centimeters approximately. Centimeters squared. So again, this occurs when x is 200 or 240 over our pi plus 4, which we said was approximately 33.6. And remember, that's what the amount of wire that's used for the square. So our total area of 126 centimeters squared occurs when 33.6 centimeters is used for the square. And the rest would be used for the circle. The rest would be 60 take away our 33.6. So 26.4 centimeters is used for the circle. So our other critical number will be again when x equals 0, which means none of it is used for the square. It's all used for the circle. So the other critical number is when x equals 0. In other words, the whole 60 centimeters is used for the circle. And so we can find out what the area of the circle will be there by letting x equal 60 in our formula that we had for area of the circle, which remember was pi bracket this will be a at 0. And the formula for the area of the circle, actually we should also check, yeah, a at 0. When x is 0, right? So if you use the formula for the circle, x is 0. Sorry, I'm just looking at this. So it's when x is 0. So you're going to have 60 over 2 pi all squared times pi. 60 divided by, in brackets, 2 pi all squared. Which is 286 centimeters squared. And when we compare that to our area above of 126, obviously that's a smaller value, right? So this is a much larger number. Okay? So this will give us a maximum area. Now you also could check one other thing, and that's when x equals, instead of 0, when x equals 60. So the other critical number when x equals 60, and I'll just tell you what that number is, which would mean that all of it is used for the square, none of it is used for the circle, is 225 centimeters squared. So if we compare all the numbers, that's the middle value. The first one we found was a minimum. The second one we found was a maximum. This one is a middle value. It's neither a max nor a minimum, because that's another critical number. Okay? You said easy? Okay, you can have these in for homework then. Page 190, questions 10 through 13, you can hand that in for homework. See how it's so easy. Yeah. I was like, okay, I was trying to make myself okay. Never lie to yourself. So this will be due tomorrow, and remember, you got your quiz tomorrow on extreme values, so intervals of increase, intervals of decrease, max and min values, as well as these word problems. And then we'll also start the chapter on curve sketching tomorrow. Do that first, then you guys will write your quiz.
Wait, Mr. Tuesday, do you take the questions out of the textbook?